Okay, so good day, everyone. Our topic for today is about shortest job first, a continuation of the CPU scheduling in our operating systems. Shortest job first is an algorithm in which the process having the smallest execution time is chosen for the next execution. This scheduling method can be preemptive or non-preemptive. It significantly reduces the average waiting time for other processes awaiting execution. The full form of SJF is shortest job first. Now, this will be the characteristics of the shortest job first scheduling. So, it is associated with each job as a unit of time to complete. In this method, when the CPU is available, the next process or job with the shortest completion time will be executed first. It is implemented with non-preemptive policy, and this algorithm method is useful for batch type processing where waiting for jobs to complete is not critical. It improves job output by offering shorter jobs which should be executed first, which must have a shorter turnaround. Okay, so this time, I will give you an example on how we'll be able to get the computation on how we'll be able to compute the shortest job versus scheduling based on NESO Academy.
Means the shortest process or the process that will require the CPU for the shortest period of time will be the first one to get the CPU. So in case of FCFS, the process that comes first was the one to get the CPU regardless of the length of that process. But in this, the length of the process matters. That means the time that this process will take in using the CPU will matter, and the shortest process or the shortest job in this case will be the first one to get the CPU. So it says here, this algorithm associates with each process the length of the process's next CPU burst. So when we say shortest job first scheduling, we don't actually mean the entire length of that process or the entire time that the process is going to take. But what we actually mean is the length of the process's next CPU burst. That means the next time this process is going to use the CPU, how long is it going to take? So for the next CPU burst, what is the length of that process going to be, or how long is it going to use the CPU? So based on that, the processes will be assigned the CPU. So the process having the least next CPU burst will be the one to get the CPU first. And this pattern will be followed for the remaining processes as well. So when the CPU is available, it is assigned to the process that has the smallest next CPU burst. So this is what I just explained. When the CPU is available, the process that has the next smallest CPU burst will get the CPU, and then this pattern will continue. Now there may be a question that comes to your mind. If two processes having the same length arrive, then which one will first get the CPU? If there are two processes waiting for the CPU and both of them have the same length, then who is going to get the CPU first? So in that case, if the next CPU burst of two processes are the same, FCFS scheduling is used to break the tie. So if that kind of a case arrive, if the next CPU burst of two processes are the same, then FCFS scheduling is used to break the tie. So that means if two processes having the same length are waiting for the CPU, then this shortest job first cannot be applied because they are both having the same length. So in that case, FCFS will be used. That is first come first serve scheduling that we have discussed in the previous lecture will be used to break the tie. That means the one that arrived first will be the first one to get the CPU, and then the next one will get after that. So that is how the tie is broken in case two processes having the same next CPU burst are there. So another very important thing that we need to know is that the SJF algorithm, that is the shortest job first algorithm, can be either preemptive or non-preemptive. So we have already discussed the meaning of preemptive and non-preemptive. So in the previous algorithm that we have discussed, which is the first come first serve scheduling algorithm, we have seen that that was a non-preemptive algorithm. That means when the CPU is being used by a particular process, that process cannot be preempted. That means that process cannot be disturbed until and unless that process completes its execution or goes to a waiting state. No other process can come and disturb it and take the CPU away from it. But in case of this shortest job first scheduling, this algorithm can either be preemptive or non-preemptive. There may be cases when it has to be made preemptive, and there may be cases it has to be non-preemptive. So in preemptive case, if one process is using the CPU, then even other processes can come and take the CPU away from it based on some conditions. So we'll be seeing that when we take the examples. So it can be either preemptive or non-preemptive. So as we discussed about the way this shortest job first scheduling works, one thing that we have to notice is that a more appropriate term for this scheduling method would be the shortest next CPU burst algorithm, because scheduling depends on the length of the next CPU burst of a process rather than its total length. So as I have explained in the beginning itself, in this SJF algorithm, though it is called the shortest job first scheduling, we are not considering the entire length of the process, but we are just considering the length of this process's next CPU burst. That means when the process is going to use the CPU for the next time. Why are we saying next time? Because during the course of a process's execution, there may be times it will use the CPU, then again come out for some IO operations, and then again use the CPU, and so on. So when the next CPU burst occurs, that means when the process is going to use CPU for the next time, what is that length going to be? That is what we actually take into account. So a better term for this algorithm would be the shortest next CPU burst algorithm. But in most of the books that you refer, it will be written as shortest job first scheduling or the shortest job first algorithm. But remember that even though it is called like that, it is actually a shortest next CPU burst algorithm. Alright. So since we have seen how it works, now let us see some examples and see how does this SJF algorithm work in case of preemptive and non-preemptive cases. So here we are going to take an example of the shortest job first scheduling when it is non-preemptive in nature. So here consider the following set of processes with the length of the CPU burst given in milliseconds. So here we are given 4 processes with process IDs P1, P2, P3 and P4, and the burst times of these processes are given, which is represented in milliseconds. So P1 has a burst time of 6 milliseconds, P2 has a burst time of 8 milliseconds, P3 of 7 milliseconds and P4 of 3 milliseconds. So in this case, let us see how we can plot the Gantt chart for this and see what will be the average waiting times for this processes if they follow a shortest job first scheduling and if it is non-preemptive in nature. So when we say non-preemptive, we mean that when a process is using the CPU, no other processes can come and take the CPU away from it. Alright, first let us draw the Gantt chart and see how it looks like. So here is the Gantt chart for this set of 4 processes if they are following the shortest job first scheduling and if they have these specific burst times. So let's see. So here what do we have to see? Since it is a shortest job first scheduling algorithm, we have to see which is the process that has the smallest burst time. So that will be the first one to get the CPU. So if you analyze these 4 processes, we see that P4 is having a burst time of 3, which is lesser than all the other burst times of the other processes. So P4 is the one that is going to get the CPU first. This is the shortest process or the process with the shortest next CPU burst. So here in this Gantt chart, we have given the first position to P4. So P4 gets the CPU first. And we are assuming that all these processes have arrived at the same time. Here the arrival times are not given. So we assume that all these processes P1 to P4 have arrived at the same time. So first of all, P4 gets the CPU because that is the one with the shortest CPU burst time. Now, how long will it execute? It will execute for 3 milliseconds. So from 0 to 3, P4 will be executed. Now after P4, which is of 3 milliseconds burst time, which is the next process having the least burst time? So from these remaining 3 processes of P1 to P3, if we check, we see that P1 is the next one, which is having a burst time of 6 milliseconds, which is lesser than 8 and 7 of P2 and P3. So P1 will get the CPU next and it will execute for 6 milliseconds. So 3 plus 6 equal to 9. Up to the 9th millisecond, P1 will be executing. So what are the remaining 2? P2 and P3. Among this, which is the smallest one? It is P3, which is 7. So at the 9th millisecond, when P1 releases the CPU, P3 gets the CPU and it will execute for 7 milliseconds. So 9 plus 7 is 16. So up to the 16th millisecond, P3 executes, and finally we have P2, which is of 8 milliseconds. So at the 16th millisecond, P2 gets the CPU and it completes its execution at the 24th millisecond, because 16 plus 8 is 24. So this is how the Gantt chart looks like for this SJF scheduling algorithm for this set of 4 processes with this set of burst times. Now let us try to calculate the average waiting times for this set of 4 processes. So since we assume that these processes have all arrived at the same time, it is very easy to calculate the waiting time for each processes. We can just see it from the Gantt chart over here. So what is the waiting time for P1? Look at P1. P1 got the CPU at the 3rd millisecond. So that means P1 had to wait for 3 milliseconds, because we assume that they have all arrived at the same time. So P1 got the CPU at the 3rd millisecond. So it waited for 3 milliseconds. Now similarly, what is the waiting time for P2? If you look at the Gantt chart, we see that P2 got the CPU at the 16th millisecond. So the waiting time for P2 is 16 milliseconds, and the waiting time for P3, similarly, if you look at the Gantt chart, we see that it is 9 milliseconds, and the waiting time for P4 was 0 milliseconds, because P4 was the first one to get the CPU and it did not have to wait. So 0 is the waiting time for P4. So what will be the average waiting time for this set of processes? It will be 3 plus 16 plus 9 plus 0 divided by 4, because we have 4 processes. So that will give us 7 milliseconds. So the average waiting time for this set of processes is 7 milliseconds. Now by comparison, if we were using the FCFS scheduling scheme, the average waiting time would be 10.25 milliseconds. So if we were using the first come first serve scheduling algorithm for the same set of processes for the same set of burst times, then we would find that the average waiting time would have been 10.25 milliseconds. So in the previous lectures, when we discussed about FCFS, we have already shown how we calculate the average waiting times in case of FCFS scheduling algorithm. So I will not be solving this same thing using FCFS scheduling algorithm again, because we have already discussed such examples before. So you can try solving it yourself, and you will find that if you solve it, you will see that using FCFS scheduling algorithm for this same set of processes, the average waiting time would be 10.25 milliseconds. So from that itself, it is clear that this SJF scheduling algorithm is better than the FCFS scheduling algorithm. Why? Because the average waiting time in case of SJF was only 7 milliseconds. But if we solve the same thing using FCFS, we are going to get 10.25 milliseconds. So which clearly shows that SJF is a better scheduling algorithm because it is giving a lesser average waiting time. And why is that? That is because if we assign the CPU to the smaller processes first, then that reduces the waiting time for the smaller processes instead of increasing it for the larger processes. So in the long run, we are going to have a lesser average waiting time. So in that way, we see that SJF scheduling algorithm is better than the FCFS scheduling algorithm. So this was the example for a non-preemptive SJF scheduling algorithm. So it was non-preemptive because we saw that when one process was using the CPU, nobody disturbed it until and unless it completed and released the CPU. No other processes were given the CPU. So it was non-preemptive. Now let us take another example of this SJF scheduling algorithm when it is preemptive in nature. So in this example, we are going to consider the SJF scheduling algorithm when it is preemptive in nature. That means when one process is using the CPU, even other processes can come and take the CPU away from it based on some conditions. Alright, let's see. So consider the following 4 processes with the length of the CPU burst given in milliseconds, and the processes arrive at the ready queue at the times shown. So here we have a table where we are given 4 processes again with process IDs P1 to P4, and here are the arrival times of these processes. P1 arrives at time 0, P2 at 1, P3 at 2, and P4 at 3. And this is the burst time of the processes given in milliseconds. So burst time of P1 is 8, of P2 is 4, P3 is 9, and P4 is 5. So all these values are given in milliseconds. So in this case, we are going to consider that this SJF scheduling algorithm is preemptive in nature. So if it is preemptive in nature, let us see what will be the average waiting time for this and how do we calculate the average waiting time for this. So the first thing that we are going to do is we are going to draw the Gantt chart for this. So let us see if we form the Gantt chart for this set of processes using SJF scheduling algorithm in preemptive way, how will it look like? So here is a Gantt chart for this set of processes, and let us see how we have formed this Gantt chart. So if you look here, we have to see what is the arrival time and the burst times. So first of all, we see that P1 was the process to arrive first. So at 0 millisecond, P1 arrived, and the burst time of P1 is 8 milliseconds. So if you look here, we may think that there are more processes here which are having lesser burst times. So why not give the CPU to that? But the problem is at time 0, only P1 was there. No other processes were there at time 0. So we directly gave the CPU to process P1. So at time 0, process P1 got the CPU. Now what happens is at time 1, so at 1 millisecond, P2 arrived. And what is the burst time of P2? It is 4 milliseconds. So we see that at time 1, P2 arrived, and the burst time of P2 is less than that of P1, which is already using the CPU. So here the SJF scheduling algorithm is going to work, because the process having the lesser CPU burst should be the one getting the CPU first. So among P2 and P1, P2 has the lesser burst time. So what will happen? P1 will be preempted. That means P1 will be removed from here. The CPU will be taken away from P1 and be given to P2. So at time 1, P2 arrived, and since the burst time is less than that of P1, which was already using the CPU was taken away from P1 and P2 got the CPU. Now let's see. P2 begins its execution. Now when P2 begins its execution, it has to execute for 4 milliseconds. So let's see. It is executing now. Now we see that at time 2, P3 arrives. Now what is the burst time of P3? It is 9 milliseconds. But 9 milliseconds is greater than P2's burst time, which is 4 milliseconds. So we are not going to preempt P2 because P2's burst time is still lesser than that of P3. So P2 will continue its execution. Now we see that P3 arrives at time 2. Now what is the burst time of P3? It is 9 milliseconds. So we are not going to preempt P2 because P2 is using the CPU, and even though P3 has arrived, the burst time of P3, which is 9 milliseconds, is greater than that of P2. So P2 is still having the lesser burst time. So P2 will still continue its execution and it will not be preempted. Now we see that at time 3, P4 has arrived. Now P4's burst time is 5 milliseconds. So P2 will not be preempted and it will continue its execution. Now another thing that you have to keep in mind here is that, see, when P3 arrives, the burst time is 9. Now we cannot say that at that moment the burst time of P2 was 4 milliseconds because P3 arrived at time 2. Now let us look at this chart and see what is the condition of P2 at 2 milliseconds. So P2 got the CPU at the first millisecond, and at the second millisecond P2 has already completed 1 millisecond of execution. So the remaining time of P2 is now 3 milliseconds. So it is not 4, but at time 2 P2's burst time will be 3 milliseconds because it has already completed 1 millisecond of execution. So similarly, when P4 had arrived, it was 3 milliseconds time. So at 3 milliseconds, what was the condition of P2? P2 had already gone from 1 to 3. So 3 of its execution was already completed. So 1 to 2, 2 to 3. So at the third millisecond, P2 already completed 2 milliseconds of its execution. So the remaining time is again 2 milliseconds. So from 3 to 4 and 4 to 5. So that was the remaining time of P2. So you have to keep this in mind when you are doing this for more processes or when the processes have a very small difference in their burst times. Alright, so we saw that even though P3 and P4 had arrived when P2 was executing, since their burst times were greater than that of P2, P2 was never preempted. So P2 had completed its execution at the 5th unit of time. The burst time was 4. So 1, 2, 3, 4. 1 plus 4 is 5. So at the 5th unit of time, P2 has completed its execution. Alright, now since P2 has completed, now the question is who will get the CPU next? Now we have P1, P3 and P4. Now who is going to get the CPU now? So let us see. What is the burst time of P1 now? It is not actually 8 now because P1 already completed 1 millisecond execution in the beginning. So the burst time of P1 is now 7 milliseconds. Keep that in mind. And P3 and P4 never got the CPUs, so their burst times are 9 and 5. So here we have 7, here we have 9, here we have 5. So which is the smallest one? It is 5. So that is of P4. So P4 is the one to get the CPU next. So when P4 gets the CPU, it executes from 5 to 10 milliseconds because the burst time is 5. And we know that no other processes have arrived after that, so it will just continue its execution and finish it. So 5 plus 5 is 10, so at the 10th millisecond P4 finished its execution. Now what is the next thing that we have? We have P3 and P1. So what is the burst time of P1? I told you here it is 7. So P1 is 7 and P3 is having 9. So which is smaller? 7 is smaller. So now P1 will again get the CPU. So P1 gets the CPU and the time it needed was 7 milliseconds. So from 10 to 17, 10 plus 7 is 17. So up to the 17th millisecond, P1 executed. And then the last one that we have is P3, which is of 9 milliseconds. So at the 17th unit of time, P3 got the CPU and it executed for 9 milliseconds, hence completing its execution at the 26th millisecond. So this is how the Gantt chart for this set of processes looks like. So we see that preemption occurred here. P1 was the first one to get it, but since a condition arose where the burst time of the next process P2 was less than that of P1, so P1 was preempted and the CPU was given to P2. And then later on when P1 got its chance, it was given the CPU again. So that is what we mean by preemptive scheduling. And this is how the Gantt chart will look like for the SJF scheduling when it is preemptive. Alright, so now let us see how we can calculate the average waiting time for this SJF scheduling algorithm when it is preemptive. So in the previous example, it was very easy to calculate the waiting times because we assumed that all the processes arrived at the same time and they were non-preemptive. So we had to just look at the Gantt chart and write down the waiting times for each of them and calculate the average waiting times. But in case of this preemptive scheduling, it is not going to be like that. For this SJF scheduling, there is a specific way to calculate the average waiting times. So let us see what is a formula that we have to use and how it is going to work. So here is a formula that we have to use. Waiting time is calculated like this: total waiting time minus number of milliseconds process executed minus the arrival time. Alright, so this is the formula and let us try to see how this formula is formed. Let us break it down and try to understand. So the waiting time is the time that a process spent waiting. So that will be the total waiting time that we can see from the Gantt chart minus the number of milliseconds the process executed. Because we saw that since this is a preemptive scheduling, there may be times when the process has already executed, like in case of this P1, it executed for 1 millisecond in the beginning, then after that it was given again and then it completed at 17 milliseconds. So here you see that at the 10th unit of time or at 10 milliseconds, P1 got the CPU. So the waiting time of P1 cannot be just said as 10 milliseconds because it has already executed some units of time over here. So 10 cannot be considered as its real waiting time. We have to subtract the number of milliseconds it has executed previously. And then we have to also subtract from it the arrival time because not all processes arrives at the same time. So from these two values, we have to again subtract the time at which the process had arrived in the ready queue. So that is how we will find the waiting time for processes in case of a preemptive SJF scheduling algorithm. Alright, so applying this formula, let us try to calculate the waiting times for these four processes and also the average waiting time. So here is the waiting times of these processes P1 to P4 based on this formula. So for P1, what is the total waiting time? If we look at the Gantt chart, for P1, the total waiting time was 10 milliseconds. So it is 10 minus the number of milliseconds the process executed. So prior to this, how long did P1 execute? If you look here, P1 executed for 1 milliseconds over here. So minus 1. And then the arrival time. What is the arrival time of P1? It was 0. So minus 0. So if you subtract 10 minus 1 minus 0, we get 9 milliseconds. That is the waiting time for P1. Now let's see for P2. What is the total waiting time for P2? So we see that for P2, it got the CPU at 1 millisecond. So 1 was the total waiting time for P2. Then how long did P2 execute before that? So we see that P2 did not execute before that at any time. So it is 0. And what is the arrival time? Arrival time of P2 is 1 millisecond. So 1 minus 0 minus 1, which is 0 milliseconds. So P2 did not have to wait for any time. It is 0 milliseconds. So see, if you look at the Gantt chart, we may think that P2 waited for 1 milliseconds, but if you really analyze it, you'll see that though P2 arrived at time 1, since its burst time was less than that of P1, it was preempted. P1 was preempted, and as soon as it arrived, P2 got the CPU. So that is why the waiting time is 0. Now similarly for P3, what is it? The waiting time for P3 in total was 17 milliseconds. And what is the number of milliseconds it executed before? There is nowhere when P3 executed before, so that is 0. And what is the arrival time of P3? It is 2 milliseconds. So 17 minus 0 minus 2 is 15 milliseconds. And similarly for P4, 5 milliseconds was the total waiting time. If you look here, P4, this is the total waiting time. And then did P4 execute anywhere before? No. So it is 0. And the arrival time of P4 was 3 milliseconds, which is given here. So it is 5 minus 0 minus 3, which gives us 2 milliseconds. Now if we calculate the average waiting time, 9 plus 0 plus 15 plus 2 divided by number of processes, which is 4, gives us 6.5 milliseconds. So this is the average waiting time in case of a preemptive SJF scheduling algorithm. So we see that in SJF scheduling algorithm, when it is preemptive, who is getting the process first? The process that has the next smallest remaining CPU burst is the one to get the CPU next. So whichever process is having the next smallest remaining CPU time. Why do I use the term remaining? Because since it can be preempted, once a process is already executed, and if it is preempted, the remaining time is what we have to calculate, like I explained in the beginning. So the process that is having the least remaining time or the least remaining next burst time will be the one to get the CPU first. So preemptive SJF scheduling is sometimes called shortest remaining time first scheduling. So this is another name that we have for preemptive shortest job first scheduling. It is called shortest remaining time first scheduling. And why is that? I have just explained that. Alright, so we saw that SJF scheduling algorithm is good and it is performing well, but does it have any disadvantages as well? Let us try to find that out and let us see what are the disadvantages of this SJF scheduling algorithm. So here we will discuss the problems with SJF scheduling. So the problem is, the real difficulty with the SJF algorithm is knowing the length of the next CPU request. So we saw that SJF scheduling algorithm is the one in which the process having the next smallest CPU burst will get the CPU first. But it is very difficult to know the length of the next CPU request. It is not very easy to find out what will be the next burst time of the process. We may be able to somehow find out the entire length of a process, but the next CPU burst of the process, that means the next time it is going to use the CPU, what is the amount of time it will take? It is very difficult to calculate that particular value. So because of that, although the SJF algorithm is optimal, it cannot be implemented at the level of short-term CPU scheduling. So even though this is an optimal algorithm, as we have seen, it is difficult to implement this at a short-term CPU scheduling level. And why is that? That is because of this. It is really difficult to know the length of the next CPU request that we are going to get. So practically there is no way to know the length of the next CPU burst. So this is one problem that we have with the SJF scheduling algorithm. So you may be thinking, if we can never know the length of the next CPU burst, how are we ever going to use this SJF scheduling algorithm? So there are ways to still use it. And let's see how it is. So what we are going to do is, our approach is to try to approximate the SJF scheduling. Now how are we going to approximate it? So we may not know the length of the next CPU burst, but we may be able to predict its value. So we may not know what is the length of the next CPU burst. Exactly, we may not be able to know it, but there are ways we may be able to predict or assume its value. That is, we expect that the next CPU burst will be similar in length to the previous ones. So once one CPU burst has occurred, then we can assume that the next CPU burst also will be approximately of that same length. So in some cases it may not be the same, but in most of the cases the next CPU burst will be somewhat similar to the previous CPU burst that we have. So we can approximate the value in that way and use the SJF scheduling algorithm. So by computing an approximation of the length of the next CPU burst, we can pick the process with the shortest predicted CPU burst. So with this approximation, we can pick the process with the shortest predicted CPU burst, and then hence we can apply the SJF scheduling algorithm in this. So that is how this problem with SJF is resolved. So that is how SJF scheduling algorithm works. And we see that it is better than FCFS scheduling algorithm, but also it has its disadvantage or problem which we have just discussed. But there is also a approach to resolve this problem. It may not be the best approach, but there is still an approach to solve this problem. So I hope this lecture about shortest job first scheduling was clear to you. Thank you for watching and see you in the next one.
Okay, so I will give you an additional example, a problem with the solutions from NESO Academy.
Solve it. So here is the problem. An operating system uses shortest remaining time first scheduling algorithm for preemptive scheduling of processes. Consider the following set of processes with their arrival times and burst times in milliseconds. So what the question says is that an operating system uses the shortest remaining time first scheduling algorithm. So we have already seen in the previous lecture that shortest remaining time first scheduling algorithm is another name for this shortest job first scheduling algorithm. And it is using a preemptive type of scheduling for the processes. And then the arrival times and burst times are given in milliseconds as shown in this table. So we have 4 processes, P1 to P4, and the arrival times are given here in milliseconds and the burst times are given here in milliseconds. Now the question is, the average waiting time in milliseconds of the processes is blank. So we are supposed to find out what is the average waiting time of these processes. And we have 4 options: A 4.5, B 5.0, C 5.5, and D 6.5. So let's see how we can solve this and how we can find the average waiting time for these 4 processes if they are using shortest remaining time first scheduling algorithm for preemptive scheduling of processes. So remember, it is preemptive. That means when a process is using the CPU, if other processes of shorter time comes, then that process will be preempted. Means a process that was using the CPU can be preempted. The CPU can be taken away from it and given to the process that has the shorter remaining time. Alright, now let us solve this problem. I have just copied down the above table here so that it fits on the screen. It's the same table. So in order to solve the problem, we have to find the waiting times for each of these processes one by one, and after that we have to calculate the average waiting times. So for that, what we have to do is we have to first form the Gantt chart for this set of 4 processes. So let us see how can we plot the Gantt chart for this set of 4 processes. So here is the Gantt chart for this set of 4 processes P1 to P4. So if we look at this table, we see that the first process to arrive was process P1 at time 0. So process P1 arrived at time 0, and then since it was the first process to arrive and since there were no other processes at that time, the CPU was given to process P1. So here in the Gantt chart, we see that at time 0, P1 arrives and P1 gets the CPU at time 0 and begins its execution. Now if we look at this table, we see that at time 2, P2 has arrived. So when P2 arrives, we see that the burst time of P2 is 4, which is less than that of P1, which is 12. So P2 has to be given the CPU. So what will happen is P1 will be preempted. That means the CPU will be taken away from P1 and P2 will be given the CPU because it has a shorter burst time as compared to P1. So at the second millisecond, P2 arrives and the CPU is given to P2. P1 is taken out. So P2 is now executing, and if you look at the table, P3 arrives at time 3 or the third millisecond. And what is the burst time for P3? It is 6 milliseconds. Now let's see what was happening in the Gantt chart. P2 was executing. So P2 started its execution from the second millisecond, and at the third millisecond, what happened? P2 completed 1 millisecond of its execution. So what is the burst time of P2? It is 4. So at the third millisecond, P2 completed 1 millisecond of its execution. So at time 3, P2's burst time or the remaining time is now 3 milliseconds. Now P2 is having 3 milliseconds to be executed, and at that time P3 arrives and the burst time of P3 is 6 milliseconds, which is greater than that of P2. So P2 will not be disturbed and it will be allowed to continue its execution. So it is continuing its execution, and up to what? Up to the 6th millisecond, because P2's burst time is 4 milliseconds. So 2 plus 4 is 6. So up to the 6th millisecond, P2 continues its execution. Now if we see at the 6th millisecond, P2 releases the CPU. So now who is going to get the CPU next? Is it P4? No, it is not P4, because the arrival time of P4 itself is 8 milliseconds. But we are only at the 6th millisecond right now. So what are the other processes that we have now? We have P1, and let us see what is the burst time of P1. Is it 12? It is not 12 now, because P1 already completed 2 milliseconds of its execution. So the burst time of P1 is now 10 milliseconds. So we have P1 with burst time of 10 milliseconds, and P2 has already completed its execution, so P2 is not to be considered anymore. And we have P3 whose burst time is 6 milliseconds. So we have P1 and P3. So P1 it is 10 and P3 is 6. So which is the smaller one? It is P3. So P3 will get the CPU at the 6 millisecond here. So P3 begins its execution, and now let's see what happens. So as P3 begins its execution, it goes from 6 millisecond to 7 millisecond, then from 7 millisecond to 8 millisecond, and at that 8th millisecond, P4 arrives, and the burst time of P4 is 5 milliseconds. So will P4 get the CPU? If you just look at this table, you may think that yeah, P4 should get the CPU because P4's burst time is 5, which is less than that of P3, which is 6. But if we closely observe in this table, we know that P4 arrived at the 8th millisecond. So let us see what is the status of P3 at the 8th millisecond. At the 8th millisecond, P3 already completed 2 milliseconds of execution from 6 to 7 and 7 to 8. So let us see what is the total burst time of P3. It is 6 milliseconds. So since it already executed 2 milliseconds, 6 minus that 2 will give us 4 milliseconds. So at the time 8, when P4 arrives, the remaining burst time of P3 is 4 milliseconds, which is less than that of P4, that is 5. So P3's remaining time is 4 milliseconds, which is less than that of the burst time of P4, which is 5 milliseconds. So P3 will not be disturbed. P3 will be allowed to continue its execution, and it will continue until it finishes. So the total burst time of P3 is 6 milliseconds. So 6 plus 6 is 12. So up to the 12th millisecond, P3 executes. Now, what are the remaining processes that we have? Let us see. So P2 has completed, P3 also has completed. Now we have only P4 and P1. Now what are the burst times? We know that P1's remaining burst time is 10 milliseconds, and P4, which has not even got the CPU once, its burst time is 5 milliseconds. So if we compare P1 and P4, the smaller one is P4. So P4 is the one going to get the CPU. So P4 gets the CPU at 12 milliseconds, and it will execute for how long? For 5 milliseconds. So 12 plus 5 is 17. Now at the 17th millisecond, the last one, which is P1, will get the CPU, and it will continue execution for 10 milliseconds. So 17 plus 10 is 27. So at the 27th millisecond, P1 completes its execution, and here we have the complete Gantt chart for this set of 4 processes. So we have to always keep in mind that this is preemptive, and whenever a process arrives, we have to closely observe what is the status of the process that is executing currently. We have to see its remaining burst time, not the total burst time, but the remaining burst time. And depending upon that, you have to compare with the process that arrives, and whichever is lesser will get the CPU. So that is how you form the Gantt chart for a preemptive shortest remaining time first scheduling. So how do we calculate the waiting times? We have already discussed the formula in the previous lecture. So this is the formula. The waiting time is the total waiting time minus number of milliseconds the process executed minus the arrival time. So the waiting time of a process is calculated by seeing the total waiting time, which is visible in this Gantt chart, and from that we subtract the number of milliseconds the process executed prior to the total waiting time, and from there we subtract the arrival time. So that will give us the waiting time for a particular process. So let us calculate that one by one for processes P1 to P4. So here are the waiting times for processes P1 to P4. So for P1, what is the waiting time? The total waiting time of P1. So let us see where is P1. P1 lastly executed over here. And what was the total waiting time? It was 17 milliseconds. So we have 17 minus the number of milliseconds the process executed prior to that. What is that? If you see in this Gantt chart, P1 already executed 2 milliseconds before coming here. So minus that number of milliseconds the process executed, which is 2 milliseconds, minus the arrival time of P1, that is 0. So if you subtract this, we'll get 15 milliseconds, which is the waiting time for P1. And similarly for P2, what is the total waiting time? We see that P2 is seen only here in the Gantt chart, and the total waiting time was 2 milliseconds. And the number of milliseconds the process executed before that, we see that P2 never executed before that. So it is 0, and the arrival time of P2, that is 2 milliseconds. So minus 2. That will give us 2 minus 0 minus 2, that is 0 milliseconds. So if you look in this Gantt chart also, we can understand that P2 arrived at the second millisecond, and as soon as it arrived, it got the CPU. So it did not have to wait. So we have 0. Then similarly for P3, what is the total waiting time? P3 got the CPU at the 6th millisecond. So the total waiting time for P3 is 6 milliseconds minus the number of milliseconds it executed prior to that. We don't have P3 before, so that is also 0. And then the arrival time of P3, that is 3 milliseconds. So 6 minus 0 minus 3 is 3 milliseconds. And then finally for P4, if you see what is the total waiting time, it is 12 milliseconds. So 12 minus number of milliseconds it executed prior to that. We don't have P4 prior to that, so it is 0. And then the arrival time of P4 is 8 milliseconds. So 12 minus 0 minus 8, which gives us 4 milliseconds. So here we have calculated the waiting times for processes P1 to P4. Now we can easily calculate the average waiting time. So the average waiting time is 15 plus 0 plus 3 plus 4 divided by the total number of processes, which is 4. And that gives us 5.5 milliseconds. So this is the average waiting time for the processes P1 to P4. So we are getting 5.5 milliseconds. So let us see if we have 5.5 milliseconds in our option. So coming back to the question, if we see the options, here we have option C, which is 5.5 milliseconds. So option C is the answer to this question. So I hope this was clear to you how we calculate the waiting times for a operating system that uses the shortest remaining time for scheduling for preemptive scheduling of processes. So thank you for watching and see you in the next one.
Okay, so this time this will be another example for shortest job first scheduling, problem number 2 with solution. Also from NESO Academy.
So here is the question. Consider the following processes with the arrival time and the length of the CPU burst given in milliseconds. The scheduling algorithm used is preemptive shortest remaining time first. The average turnaround time of these processes is dash milliseconds. So what we are given in this question is that we are given a set of 4 processes with process IDs P1 to P4 with their arrival times given here in milliseconds and their burst times given here in milliseconds. And we are told that the scheduling algorithm used is preemptive shortest remaining time first. So this is another name for the shortest job first scheduling, and what we have to keep in mind that it is preemptive. That means when one process is executing, if another process of shorter burst time arrives, then the executing process can be preempted or the CPU can be taken away from it and given to the shorter process. So that is what it means. So the main question that we have is we have to calculate the average turnaround time for this set of processes. So we have already discussed what is turnaround time. So we have to calculate the turnaround time for these 4 processes and we have to see what is the average turnaround time. And we have 4 options: A 8.25, B 10.25, C 6.35 and D 4.25. Alright, so let us see how we can solve this problem. Alright, so I have just copied that table down here to make it fit on the screen. So let us see how we can solve it. So the first step in solving this kind of questions is to form the Gantt chart for the set of processes that we have. So let us see how we can form the Gantt chart for this set of 4 processes P1 to P4 if they arrive at these arrival times, and if they have these burst times, and if they are following a preemptive shortest remaining time first scheduling. Alright, so here is a Gantt chart. Now let us see how we have formed this Gantt chart. So first of all, let us see in this arrival time, which is the first process that arrives. So we see that P1 is the process that arrives first. It arrived at the time 0. So at 0 milliseconds, P1 arrived. So since it is the first process to arrive, and since there were no processes at that time shorter than P1, so the CPU is assigned to P1 directly. So P1 begins its execution. And which is the next process to arrive after P1? So the next process to arrive after P1 is process P2, and we see that P2 has arrived at time 3. So at the 3rd millisecond, P2 arrives. Now let us see what is the burst time of process P2, and let's see if P1 will be preempted. So we see that the burst time of process P2 is 6 milliseconds. And what is the burst time of P1? The burst time of P1 is 10 milliseconds, but we see that P2 arrived at the 3rd millisecond. So at the 3rd millisecond, P1 was already executing, and it has completed 3 milliseconds of its execution. So from the total burst time of 10 milliseconds, P1 has already executed 3 milliseconds. So what is the remaining time for P1? What is the remaining burst time for P1? It is 7 milliseconds. So the remaining burst time of P1 is 7 milliseconds, and the burst time of P2, which has arrived at the 3rd millisecond, is 6 milliseconds. So which is smaller among these? We see that P2 is obviously smaller. 6 is smaller than 7. So P1 will be preempted and P2 will be given the CPU for its execution. So here we see that at the 3rd millisecond, P1 is preempted and P2 is given the CPU. And how long will P2 execute? The burst time of P2 is 6 milliseconds. So let us see if it will be allowed to continue its execution or what will happen. So if we see the next arrival time, the next process to arrive after P2 is process P3 that arrives at the 7th millisecond. So let's see at the 7th millisecond what is the condition of P2. So the burst time of P2 is 6 milliseconds and it began its execution from the 3rd millisecond. So from the 3rd millisecond we have 3, 4, 5, 6, 7. So from 3 to 4, 4 to 5, 5 to 6 and 6 to 7. So 4 milliseconds of execution is completed for process P2. So what is the remaining burst time for process P2 at 7 milliseconds? It is 2 milliseconds. So the remaining burst time for P2 at the 7th millisecond is 2 milliseconds. And at that time P3 had arrived. And what is the burst time of P3? It is 1 millisecond. So among P2 and P3, which is the smaller one? We see that P3 is obviously the smaller one. It has only 1 millisecond of burst time. So P2 will also be preempted and P3 will be given the CPU. So we see in the Gantt chart that at the 7th millisecond when P3 arrives, P2 is preempted and P3 gets the CPU. And P3 executes for 1 millisecond. And after executing for 1 millisecond, we see that in this arrival time, at the 8th millisecond, the next process arrives, which is P4. And what is the burst time of P4? It is 3 milliseconds. So we see that P3 already completed its execution because it had only 1 millisecond of burst time. Now the processes that we have are P4 with 3 milliseconds and P2 which has a remaining burst time of 2 milliseconds and P1 which also has a remaining burst time of 7 milliseconds. So which is the smallest among these three? So we see 7, 2 and 3 here, and the smallest one is obviously 2. So P2 will be the next one to get the CPU. So we see that after this P3 releases the CPU at the 8th millisecond, P2 gets the CPU. And how long will P2 execute? It will execute for 2 milliseconds because that is its remaining burst time. So P2 executes from 8 to 10 milliseconds, and after that P2 will release the CPU. And who is the next one that will get? So the remaining processes that we have are P1 with a burst time of 7 milliseconds and P4 with a burst time of 3 milliseconds. So which is smaller among these two? It is obviously P4, it has a burst time of 3 milliseconds, which is smaller than 7, which is of P1. So P4 will be the next one to get the CPU. So at the 10th millisecond, P2 releases the CPU and P4 gets the CPU. And how long will P4 execute? It will execute for 3 milliseconds. So from 10 up to 13. 10 plus 3 is 13. So up to the 13 millisecond, P4 uses the CPU and then it will release the CPU. And what is the only process that is left now? That is P1. So finally P1 will again get the CPU at the 13th millisecond when P4 releases it, and P1 will execute for 7 milliseconds. So 13 plus 7 gives us 20. So at the 20th millisecond, P1 completes its execution, and here we have the full Gantt chart for this set of 4 processes P1 to P4. So whenever we have this kind of problems, it is crucial to form the Gantt chart, whether you are calculating the average waiting time or the average turnaround time or whatever it may be. So once we have formed the Gantt chart, it is very easy to proceed with the remaining portion of our calculation. Alright, so now we have the Gantt chart, and what we have to calculate, our original question was to calculate the average turnaround time for this set of processes. So for that, we have to first calculate the turnaround time for these processes one by one. So what is the formula for turnaround time? So the formula for turnaround time is completion time minus the arrival time. So we know that turnaround time is actually the time that the process takes for its entire execution, including the time it was waiting. So the turnaround time will be the completion time, the time when the process
Okay, so I think that this will be the example of the computations in getting the shortest job first. No, so this will be the advantages of using shortest job first. No, SJF is frequently used for long-term scheduling. It reduces the average waiting time over first in, first out algorithm. It SJF methods gives the lowest average waiting time for a specific set of processes. It is appropriate for the job running in batch, where run times are known in advance. For the batch system of long-term scheduling, a burst time is estimated can be obtained from the job descriptions. For short-term scheduling, we need to predict the value of the next burst time and probably optimal with regard to average turnaround time. What is the drawbacks and cons of the SJF algorithm? So job completion time must be known earlier, but it is hard to predict. It is often used in batch system for long-term scheduling. SJF can be implemented for CPU scheduling for the short term. It is because there is no specific method to predict the length of the upcoming CPU bars. This algorithm may cause very long turnaround times or starvation, requires knowledge of how long a process or job will run, and it leads to the starvation that does not reduce average turnaround time. It is hard to know the length of the upcoming CPU request, and elapsed time should be recorded. That results in more overhead on the processor. So again, the SJF is an algorithm in which the process having the smallest execution time is chosen for the next execution. SJF scheduling is associated with each job as a unit of time to complete. This algorithm method is helpful for batch type processing where waiting for jobs to complete is not critical. There are basically two types of shortest job first methods, non-preemptive and preemptive. If non-preemptive scheduling, once the CPU cycle is allocated to process, the process holds it till it reaches a waiting state or terminated. In preemptive shortest job for scheduling, jobs are put into the ready queues as they come. Although a process with short burst time begins, the current process is removed or preempted from execution, and the job which is shorter is executed first. Shortest job first is frequently used for long-term scheduling. It reduces the average waiting time over first in, first out algorithm. In shortest job per scheduling, job completion time must be known earlier, but it is hard to predict. And it can be implemented for CPU scheduling for the short term. It is because there is no specific method to predict the length of the upcoming CPU burst. And that's it for shortest job first. Thank you, and please prepare for our quiz. Good day. Keep safe, everyone.